I think I need to thank Martin for raising the issue of anisotropy, because the whole talk is actually about anisotropy of solid-state granular materials. I have to say I came from civil engineering and chemical engineering, so I know nothing about rheology. The talk is nothing about rheology, not about viscosity. But I think that's kind of common interest, trying to link the two ends together. So why we are interested in directional statistics? So soil mechanics basically is kind of experimental arranging at like 100 years ago. So what we do, we want to analyze the deformation and strength of infrastructure. So we do need the stress-strain relationship for every local point. So loads of experiments have done. And as we have more advanced equipment, have more observations, the constraint modeler is just getting more frustrated. The main reason is the soil behavior is really sensitive to a lot of factors. Whenever we change the density, whenever we change the loading direction, even we share a different mode, the response is totally different. So how could we just came up a beautiful theory to describe all this behavior? So I'm not going to cover the whole range of behavior, but I just want to point out that the influence of material anisotropy. So this, what I'm showing here is equipment in soil labs. So the idea is we can rotate one plate on top, that gives a shear, and we can control the inner pressure, out pressure. So that gives us additional freedom to control the principal stress direction. So if you think about a block on table, basically the direction you apply force should be the direction the block sliding. But unfortunately for soil, even if we apply loading in this direction, the deformation may not be in that direction. So this is a big problem for classical plasticity theory, because if we don't know the stress direction, we don't know strain direction, we don't know how to do it in the boundary condition problems. So I'm just trying to show you how the soil behavior can be different when we change the loading direction. This is the Andrin test, which is constant volume sharing. And this set of theorem curves is experiment carried out on identical sample. The only changing parameter is actually loading direction respecting to the bedding plane. So you can see we have a very soft behavior, or we can have a very strong behavior. So we need to understand that, and then we can possibly model it. And so about deformation non-coaxiality is what the terminology we use to describe the non-coincidence between the stress direction and the strain increment dimension. That first discovered by Roscoe in 1970 is a very classical problem. And later on, we did some DM simulation recently. It's even getting more complicated. We have two specimens which actually have similar anisotropic structure at initial state, but when we share it at different directions, the observation of non-coaxiality is actually different. So in these two plots, these vertical lines is the strain increment direction, and these symbols give you the stress direction. So why we have similar isotropic structure and totally different response? So that's a question I asked myself about 3-4 years ago. And following the line, say, with all this difficulty trying to came up a constraint model to describe soil behavior, and then there are a group of theorists trying to say, even the material behavior is quite complicated, the concept interaction is quite straightforward. Is there any chance we can derive this whole set of theory based on particle information and particle interaction informations? So this is kind of dream we want to achieve. It's quite challenging. I think with 20-30 years continual efforts, we haven't arrived there yet. But good thing is in last 20 and 30 years, we have a lot of development and experimental development with the observation, like the PIV and the image analyze, and we have CT scanning, and also we have a numerical technique, discrete element simulation, and we are quite lucky. So even we have very idealized system, many of the features we observe in soils can be reproduced using DM simulations. So it's becoming a little bit more promising, trying to achieve that challenging. In order to do that, we have to, because at the particle scale, everything we have is contact forces and displacement. We may have a reasonable assumption of simple contact model to describe the relationship between these two. And at macro scale, we use stress and strain tensors. and we want to study this continued relationship. So one thing has kind of been established in last few years, at least last 2 decades, is the internal structure. We know internal structure had to be there and very important there. So there are some achievements on the theoretical side. So these 2 equations may be a little bit complicated, but actually it's quite rigorous sets established. This equation gives a relationship of the stress tensor on the particle contact forces and the local contact vector. It's local geometries. The setup in this equation is only based on Newton's second law. And as long as we have a simple element which can be considered uniform, that's valid. So another work about strain that's kind of accomplished now as well. So this equation is actually trying to set up the macro strain tensor with micro particle in relative displacement. So every local macro stress-strain relationship can be linked to force and displacement. That's the first thing. But you probably can see the problem now. So originally we have one stress tensor, one strain tensor. We won't set up them 2. But if we want to study things from particle scale, that means we have millions or tens of millions information about contact forces, displacement. So it's not kind of trivial thing just to link them up together. So that's the thing I realized that we need statistics and we need direction statistics. That's kind of title of today's talk. If you think about vector thing, if we add many vectors together, if they're symmetric, they vanish. So that's a problem. We couldn't use the classical statistics theory, use scalar values. And we're quite lucky because we find a very good paper in 1984 by Calatani. So what he introduced to say, if we have many vectors, like if think about the particle orientations on contour normal vectors, if we want to describe it, we may borrow this idea about this series. So this is kind of similar to Fourier series. The only thing is now the variable is not x, it's a vector. It's a vector to give us directions. And then this d is a tensor, is a coefficient. So if we have a group of this discrete data, we borrow these forms. If we can determine this coefficient, we have approximation of this direction distribution. So we can do it. So basically, as long as we have group of discrete data, we can follow his theory to determine this coefficient tensor based on the minimum least square error method. But it's not sufficient if we want to study more complicated forces distribution, because force is a direction and a magnitude. So we borrowed his spirit, but only thing we say, we're trying to characterize along each direction how is the average contact force distributed. So this is very mathematical. I don't have time to go to details. Actually, I'll come back and then we actually have a little bit problem here. So anyway, we have a method. We derived the mathematical skills. We can calculate the coefficient tensor to describe the direction distribution, not only the contact normals, but also contact forces and displacements. So this comes back to another thing. How could we use this mathematical tool to answer our problem? So this is another very clever guy, Rosenberg, and he had this idea in 1980s. He is saying, the stress tensor is a summation of many contact points. Every contact has a direction. So if we subgroup contact according to direction and do the integration, we can get a stress tensor by getting this directional integration. So now you can see the connection between his theory and direct statistics. Using direct statistics, we can get these directional functions, and then to get the stress tensor, we just need to do the integration. So, when Rosenberg derived his work, I don't think he has this directional statistics theory available. So he has a lot of assumptions trying to simplify this process. Eventually, he came up with this expression. So in two-dimensional case, the minimum stress and the stress ratio can be linked direction to these parameters from this direction tensor. Now we can do a little better with the direct statistics theory. First, we can check. So one of the first assumptions he assumed is that in each direction, the contact vector and the contact forces are statistically independent. So that way, we can just break this down term as the summation of this term among and multiplication. So with the directional statistic, we can check is it reasonable or not. So our conclusion is not exactly statistically independent. In each direction, there is some slight correlation between. But along each direction, its direction distribution is okay. So in order to characterize this directional statistics, we introduce a scalar vector here. Sorry, scalar here, no vector. And then what we can do is, ideally, if we have many, many terms, any kind of direction distribution, we can describe it. But we may not necessarily need it. So we can use discrete data to say we can calculate tensors, and we can plot it out. It's quite simple in 2D case, because in 2D, any rank-1 tensor only have one scalar variable in one direction. So we can plot it out. So this is the result from DM simulation. You can see quite straightforwardly, only the second rank term is significant. So that means we only need to keep this term. So that equation becomes the same as what Rosenberg proposed initially, with very good physical insight there. So we can do the same thing for forces. This is a vector. It takes a little bit of time. But again, for forces, we only need to first two terms, like GJI on the third rank term there. And then by keeping these two terms, that means we kind of trunked the infinity series of terms there with very limited terms. And with the benefit of direct statistics, it helps us to do the integration. So if we substitute this whole phenomenon to do direction integration, actually direct statistical theory help us to simplify into that term. So yeah, we can do that. And now we use our observation in DM simulation. We keep only these terms. That helps a lot to simplify this equation. So this is what's simplified from the previous integration term. And there is a very lucky phenomenon in 2D. Many terms are actually, so if we, this term, we can keep it, but there are many terms, they are actually unsymmetric. I don't know why, but when I do the multiplication of these tensors, because they are divitoric, they're symmetric, they actually give us a symmetric tensor. But if the problem we are studying is mainly causes stress tensor, it has to be symmetric. So that tells us this term, again, I can simplify it as a scalar. So finally, here comes the two-dimensional stress-force relationship. So this is a scalar, give us the contribution of these higher rank terms, and originally I only have these three terms. They are divitoric and symmetric. And if we look into the mean normal stress, this term gives us information. If we look at divitoric part, it's mainly contributed by anisotropy of contact vector, anisotropy of contact force, and anisotropy of contact normal distribution. So with all of that, let's go back to have a discussion about deformation non-causality. This figure just shows the expression I provide here give us almost exactly same result as the stress and strain we get from the boundary. So let's give us additional confidence how good this relationship can give us information. So let's look into deformation non-causality. So now here stress tensor it actually depends on these three divitoric tensors. These two terms, contact vector, it depends on particle shape, and this one is contact normal distribution. They are geometric. So we kind of say now we have confidence. This is the fabric tensor should be looks like. It has two contributions. One is because the particle is non-spherical. The other is its packing. Its packing in space is unsymmetric, and we have this divitoric tensor to describe it. And we have another divitoric tensor to describe contact forces. So now this term gives us the divitoric stress tensor, and we can determine its direction. So this expression gives us the direction of stress tensor, which actually only have two influential parameters. One is the relative magnitude, the ratio of magnitude of these two divitoric tensors. The other is their difference between their directions. So this one becomes theoretical, established, and we can plot it. So horizontal axis give us the difference of their directions, and I plot in this figure the ratio of these two magnitudes. So if the magnitude of this ratio is quite small, we can say actually non-causality, the degree of non-causality is quite small. even the fabric anisotropic magnitude can be large, but as long as the ratio is small, the degree of non-causality is small. And then if the degree of the ratio is large, even though the fabric anisotropy can be small, we can have like as large as 30 degrees of deformation non-causality there. So is that same as what we observe in DM? So this figure gives us the ratio of the two magnitudes. This one gives the direction difference. So if this one is actually the sample we have observed very small non-causality, is around 0.2, 0.4. So no matter what kind of the direction difference, that gives us a very low deformation non-causality. And this one, the preloaded sample, somehow it has a very strong, very high ratio of the fabric and the force anisotropy. So that explains the high degree of non-causality we observed for this sample. So this seems quite theoretical, but actually in our group we have like parallel discrete element simulation and experimental work. Is kind of give us good confidence that is the reason behind everything. So I'm just jumping to the conclusion. I think I'll skip that for time limitation, but I really need to raise one thing. So we did that theory for 3D should work, but we don't very lucky for 3D comparing 2D. There's still a lot of time remaining in 3D, but really we want to accomplish this problem for soil mechanics. We want to be practical. So if there's any mathematician sitting in the ground and who is interested in the work, and please come to me. I really need some help here. And finally, thank you for your attention.
This contact distribution, that's a constitutive component that you feed in to your model. Have you considered allowing that to be a degree of freedom?
What do you mean by a degree of freedom?
Well, in the sense that under loading, this contact distribution itself would have an evolution, relaxation.
Yeah, we have observed, we plotted the fabric evolution, including coordination number and the fabric anisotropy. I think it's kind of the same as many soil mechanics people observe. It continually increase and approach like constant value at a high strength level, and that anisotropy is kind of independent of lot of influential factors.
This could link what you're doing to the rheology questions, because in some sense that gives you rheology if that's an active degree of freedom.
Yeah.
If you look, there's a lot of work being done using area stress functions and discrete calculus for characterizing, ensuring that the stress tensor is symmetric and in force balance. Have you looked at any of that work to use those ideas?
The symmetric of stress tensor?
Well, the stress tensor's got to satisfy equilibrium conditions of force balance, and one way of doing that is you use a stress function, and then you need to then define that in a discrete way on the net of contacts, and then you can do that in 2D and 3D. And there's been lots of papers on that.
I think this expression is actually, I'm not sure about this stress equation is actually from those discrete analyzers.
Yeah, but this is using, rather than writing it out directly, you write it in terms of potentials.
Oh.
Write it in terms of a vector potential, then you can get it to satisfy everything automatically. So you're getting rid of all of these constraints, which are the problems in this.
Yeah.
Probably the things that make it very difficult. And you can do this in 3D, and then without the constraints, all of your variables are appropriate.
Yeah, I think because the Cantani, he pointed out this, the technique is actually kind of spherical harmonic scales in 3D, so that could fit in well the potential function something. Yeah.
I have a question, actually. You mentioned that when you preload the sample, you actually get an increase in sort of non-coaxiality. Is that right? Yeah. Which way are you actually preloading the sample? I mean, what's the actual preload? Is it in the same direction as what you then load, or is it a normal to that, or?
So the two samples, one is like I just normal deposition process. I got one sample, this is the first.
So when you deposit it, is that, when you say normal deposition, is that anisotropic fabric?
Yeah, it's anisotropic.
So that's like a sedimented.
Yeah. And then for the preloading, I basically apply the ring vertically. So the fabric actually increase. But then I kind of unload it to isotropic stress. The fabric kind of decreased to a very small value. So if we compare these two fabrics at isotropic stress state, they are quite close. So that is the reason I really that
so
body
close in terms of the stress state, but they give a very different coaxiality in terms of the constitutive relationship. Is that what you're saying?
They give very similar information about fabric entropy, but in terms of deformation non-coaxiality, they're quite different.